Marko Horvat, and it's joint paper by Čačić, Horvat, and Iljazović.
Yeah, so
it's a little bit of topology.
Yeah, hopefully it
constructive topology.
It will. I'll be able to convey the general message at least. So, hi everyone, and thanks for coming to my talk. This is, as Professor Čačić said, joint work with Vedran and Zvonko. And speaking of Zvonko, so with his doctoral student Bojan Pažek, 3 years ago he managed to prove a very nice theorem about computable metric spaces and some very strange but very nice subsets of them. So what's a computable metric space, if you've never heard? So basically it's a metric space XD equipped with a dense sequence in X, so that if you take the function that takes a pair of naturals ij and maps it to the distance between alpha I and alpha j is recursive. Okay, so this is a computable metric space, and basically you can think of it as, you know, you're trying to measure the distance between 2 points. You should be maybe happy with only managing to compute the distance between alpha I and alpha j that are fairly close. Okay, so you can approximately measure in this sense. Okay, and now let's say you have a set S, a subset of X, which is a continuum. Okay, this is going to be a problem, I see already. Okay, so imagine that S is a continuum, as I said, so basically compact, connected, and metric. Okay, and okay, so another property that S might have is it may be decomposable. Okay, so decomposable basically means that it can be represented as the union of two proper subcontinua. Okay, so this is decomposable. And let's say that it's also chainable, which means that it can be completely covered by a chain. And the chain is simply a finite sequence of sets, any kind of subsets of the space. The thing is, chainable means that the chain can be as fine as you want. Okay, so for every epsilon greater than 0, you can cover the continuum here with links of size at most that. Okay, so diameter of size at most that. Now the yeah, this is a bit annoying. Okay, so each link. So what's the definition of link? So basically, each link intersects itself, which means that simply that it's non-empty. Okay, every two adjacent links have a non-empty intersection. However, if they're further apart than, you know, 1 index, then the intersection is empty. Okay, this is the defining relation. Okay. So this is sort of, I guess, natural, what you would want to be a chain, right? So if you have, as I said, a computable metric space and such a weird subset, okay, decomposable, chainable continuum, and if it turns out to be semi-computable, which I'll get to in a second, then for every epsilon greater than 0, there exist computable points A hat, B hat in S, and a computable subcontinuum S hat of S, such that S hat is epsilon close to S, and S hat is chainable from A hat to B hat. Okay, so this is basically saying that you can approximate a semi-computable continuum which has these properties with a computable subcontinuum from one computable point to another. Okay, and when I say chainable from A hat to B hat, I mean whichever epsilon greater than 0 you take, and there's, you know, very fine chain, you can always put the A hat in the first link and the B hat in the last link. Okay, good. So this is already proven in 2018. And chainable, as I said, you can go as fine as you want. Okay, so here's a finer one. So and this epsilon closeness, I'm not sure if you're familiar with the Hausdorff metric, but the idea is, so there's no outliers greater than epsilon. Okay, so for each x in S, there exists a y in S hat such that the distance is less than epsilon. Okay, And sort of conversely, I guess, or vice versa, for each x in s hat, there exists a y in s such that their distance is less than epsilon. Okay, so no outliers basically. But so the red stuff is basically what needs to be changed, or rather somehow tweaked to fit into the topological setting better, right? So we won't have a computable metric space, we'll have a computable topological space, okay? A continuum will now be a Hausdorff continuum, which basically means not compact connected metric, but compact connected Hausdorff, okay? And of course, we don't have the luxury of epsilons and epsilon plus, right? So we'll say that for each open cover U of the underlying topological space, there, you know, S hat is U close to S, which will mean basically the same thing in terms of, you know, quantifier alternation, but X and Y won't be less than epsilon close. They will simply be in the same element of the open cover, okay? And this in metric spaces is equivalent, okay? So for every epsilon being epsilon close is equivalent to for every open cover U being U close, okay? Good. So somehow it makes sense to say it in this way. And so the paper has been accepted a week ago or so, and I just don't know if it will be published this or next year. I don't know. But anyway, so let me tell you now what a computable topological space is. So it's a topological space with a countable base, okay, and many conditions need to be satisfied. But you know, maybe for the topologists around. So basically, you might think that you know, our proof is a hoax because we are talking about Hausdorff continua, which are among other things compact Hausdorff, and also second countable, obviously, because there's a countable base for the whole space, so also for the subspace. I won't be saying subspace the whole time because it's annoying. Okay, I'm sure you'll figure out what needs to be compatible with what, or induced topology or something like that. So compact, compact Hausdorff and second countable means metrizable. Okay, so how come the earlier result doesn't work already for our setting? Well, the thing is that the computable topological space that turns out to be metric is not necessarily a computable metric space, okay? So it is separable because it's compact metric, obviously, okay? So it has a dense sequence in there, okay? But it the function that maps the two naturals to the distance between the alphas, okay, that one doesn't need to be recursive. And this small subtlety leads to the 12-page proof that we had to do in order to transfer the thing to the new setting. Okay. So, okay. As I said, we have a topological space and we have a countable base. And now XT with this countable base is a computable topological space if there exist computably enumerable relations C and D on the naturals, such that C is basically a computable or effective version of containment between base elements. Okay, so if I have ICJ, then I also know II is a subset of IJ. Okay, the converse doesn't necessarily hold. So just because it's true that II is a subset of IJ, it doesn't mean I'll be able to, you know, have a program which will then allow me to verify this. Okay, maybe this is unattainable on a computer, for example. However, these relations can be made too small, as I'll comment a bit later. So D is a sort of effective disjointment, okay, disjointness, sorry. So if IDJ, then II is disjoint with IJ, okay. Now the third thing is if I have two base elements and an X in the intersection of them, then I can find an IK, or rather K in N, such that IK is effectively contained in II and ij, so kci and kcj, and also ik, of course, is around x. Okay. Now the fourth thing is sort of effective Hausdorff property. Let's put it like this. So if I have x and y, which are different, then I can find I and j in n, such that ii and ij contain x and y respectively, and idj, so they are computably disjoint. Okay. Now these four properties and the countable base, these sort of form the definition of computable topological space as Vedran put it for SCT2 space. So the main sort of tweak that you can do here is you can augment C and D or extend them in a way where you will be able to preserve all these properties along, of course, with the most important one, which is computable enumerability, right? And get some additional properties. So you can always make D symmetric, which is also what you would want out of effective disjointness. You can always make C reflexive and transitive, and you can always, if you have, let's say, II and effectively disjoint ij, and an effectively contained ik within ii, then these two guys are also going to be effectively disjoint. Okay, very natural stuff. So you can also take this as our definition of computable topological space if you want. In any case, you can use 5, 6, and 7. These here are called, so if C and D have properties 1 to 4, they're usually called characteristic relations of a computable topological space. And all of these 1 through 7 are called proper characteristic relations. Okay, usually you want those. So in the proof, we actually use transitivity to a huge degree, and I'll probably even comment on it a little bit later. So I still owe you the definition of computable points and sets, or semi-computable. Let bracket be a recursive function which enumerates all non-empty finite subsets of N. Okay, so basically, when you go through J and N, then bracket J goes through all such sets. Okay, a surjective function. Okay, onto. So let's fix a computable topological space, and for some J in N, we define JJ as the union of I in J bracket II. Okay, so basically, so JJ are simply all non-empty unions of base elements. Okay, non-empty finite unions of base elements. So maybe, I don't know, J50 is I3 union I17 union I30, simply because bracket 50 is the set 3, 17, 30. Okay. So now for a point X in X, we say that it's a computable point in the computable topological space if we somehow understand it well enough to know, to be able to verify which base elements it's contained in. Okay, so if the set of all I in N such that X is in II is computably enumerable. Okay. Now a set S is computably enumerable, or CE for short, in the computable topological space if S is closed in the underlying topological space, and the set of IIs that intersect S is computably enumerable. I should always be saying, you know, the set of all indices of these base elements, but it's cumbersome, so I won't. Okay. So basically, what are you doing? You're kind of shoveling through S with the help of these IIs, and you'll be able to pick up all the elements in S. However, the shovel is, you know, however fine-grained the base you have. Right? S is semi-computable in the computable topological space if S is compact. And the set of all base elements J, or rather, sorry, of unions of base elements J that contain S is computably enumerable. So you can basically have a printer, you know, that kind of gives you every time some set that's made through a finite union of I's that contains the whole of S, right? And you know, you can think of it as, you know, maybe it's growing, maybe it's shrinking, but kind of if you want to tighten a J as much as possible around S, maybe you can wait for a while and then, you know, be happy with what you get, right? So you're sort of approximating the set from the outside. Okay, and S is computable if it's semi-computable and CE. So maybe just one thing to note: don't confuse computably enumerable subsets of the naturals with computably enumerable subsets of the a computable topological space. Okay, so I'm using this CE the whole time as, you know, for naturals, and here I'm defining it for computable topological space. Okay. Just two more, let's say, variations on the theorem that we're trying to prove, which will allow us to somehow fix the, you know, what we kind of introduce here. We'll fix it with corollaries later. Okay, so this is just to sort of help kickstart the proof more easily. So first, a simplification. So let's say that the ambient space X is equal to S. So we don't start with, you know, a huge X and then look at our continuum in there. We simply start with STII, which is a computable topological space, but also happens to be a semi-computable, decomposable, chainable Hausdorff Continuum. Okay, and then we have the conclusion that we talked about. So for every open cover U of the topological space, there exist computable points A hat, B hat in S, and the subcontinuum S hat, which is also computable, U close to S, and chainable from A hat to B hat. Okay. Now, this decomposable I put in red simply so that I can just fix one decomposition, and then from that I'll be able to prove the whole theorem. Of course, I won't be doing that now, but I'm just saying this is more of an advertisement for the paper, nothing more. So if we take this STII and let it be a semi-computable chainable Hausdorff continuum, where K1 and K2 are subcontinua which produce S in the union, and we have 2 points, A, which is outside of K2, and a point B, which is outside of K1. Okay. Lastly, we have 2 base elements around A and B, which are sort of pretending to be a small epsilon. Okay, the idea is to get the A hat and B hat points to be within these small, let's say, base elements around A and B. Then there exist computable points A hat, B hat in S, and the computable subcontinuum S hat of S, such that A hat is in I alpha, B hat is in I beta, as I said, and S hat is chainable from A hat to B hat. Okay, so here is just the copy-pasted theorem with some words, you know, made to fit in 4 lines. Now, I'll explain the construction stages, and let me now just say, so as I said, we are in a metric space, but not in a computable metric space. This means that our construction is going to use topology only. Okay, so we're going to use sort of small, effective, computable topological steps in the construction itself. Okay, because we need this, let's say, we need to preserve the computability aspects. But later, when we prove stuff about this, okay, then we'll go down and dirty with any kind of metric stuff, epsilons, Lebesgue numbers, and so on. Okay, so this is no problem. This is a metric space, but it's not computable metric. That's the main sort of takeaway, I guess. Okay, so the construction stages. So we sort of start, and I apologize for how hideous these pictures are in the continuation, also for the previous ones, but these especially because I drew them in like a few minutes. I had very little time. I had to catch the plane. So and now I don't have my graphical tablet with me. So anyway, I alpha and I beta are around A and B, which are in S. And now we're trying to find A hat and B hat and S hat, which are all computable, right? So how do we do this? So we have the 2 continua, K1 and K2, that make up S. And A and B are outside the respective one. So A outside K2 and B outside of K1. And the intersection can be, you know, something. It doesn't have to be empty. It's fine. We sort of augment both K1 and K2 to JA tilde and JB tilde. But so they're going to be fairly large in some sense, but still B, because it was outside of K1, and JA tilde is a sort of a blow up of K1, we still want B to be outside. Okay, we can find such sets, JA tilde and JB tilde. And what we want to look at is the set of all chains that cover S, but we'll mostly be concerned with the links that are both in JA tilde and JB tilde in this effective sense, so in the sense of C. Okay, so before we had K1 and K2, we couldn't even talk about C, but now that we have just the base elements and their unions, we can actually talk about, you know, effective containment, right? So I have two more links on the left and right, these jagged ones, which we won't care much about, but I just want to note that so the first one, sort of the inner ones are small as the chain, but the outer ones are sort of like elephant ears, which we put so that we can actually cover the whole thing. So the idea is going to be to find the points and the subcontinuum by squeezing, okay, by sort of intersecting. And the thing is, when we go finer and finer and finer with this chain and its links, then sort of the whole thing is going to shrink to the middle, okay? And then we'll need a flexible sort of outer layer that will allow us to still be able to cover the whole of S, okay? Okay, so once we have this situation, we can then, in a clever and long-winded way, recursively select a falling sequence of these chains, okay? And then we'll do the intersection, as I was saying, okay? Intersection of the middle links. So this J, Ln, whatever, these are just the round middle links, okay? And right, so if you know topology, then you know that what you want to do is you want to take the closures of each, you know, level, and then you want to intersect them so that you get something in the limit, okay? So in the intersection, you then get something. However, you then mess up the computability completely in principle, okay? What we managed to do in our construction is we have each level, let's say this 0th level, okay? We have it contain in the computable sense, let's say the billionth level, along with the closures, okay? So, also the first level, sort of the first finer, smaller chain, is going to contain, let's say, the, I don't know, 2 billionth level or whatever, okay? And then again with the closures. So the intersection with or without the closures is going to be exactly the same, okay? So we also proved that the links that they that the diameter of the links goes to 0 with going further down and down. And this is why we were a bit scared when proving this. So A hat and B hat are the only, so these links, the first one and the last one, the round ones, they are going to fall within themselves, as you see, okay? So it's the intersection of just this first link and the last link in through the levels, okay? And then in there, because the diameter of the links goes to 0, as well as then the diameter of the closures goes to 0, then you will have a single point in there. And now it's either computable or it isn't. So we were lucky to find that they are computable, and indeed we get what we wanted, right? So this is sort of, yes, again, I apologize for how ugly this is, but sort of, so these links fall within themselves, okay? And this S hat, comes about from extremely meandering, possibly, super fine chains in there, which makes the whole thing very complicated, but it checks out, okay? Somehow it checks out. So the important thing is to have this kind of topological refinement, which means that you know, on the billionth level, the small link with the closure needs to be the whole of this, the whole closure needs to be within a single link on, say, the 0th level, right? So you need to have just, you know, you put the whole thing with the closure somewhere in either the 50th link or the 3rd. You can't have, you know, a situation where you have a, here. You can't have a situation where you have 2 links, okay, 2 links, and then you have one that kind of is neither in one, the whole of it, and not in the second one also, okay? So you need usually to go a bit slower through the intersection of them so that you always have this kind of topological refinement, but we require the effective refinement. You need to go through the relation C, okay? This is very important. And as you can see, so chains are defined through basically these, okay, levels. You have containment, and chains are defined with respect to disjointness, right? So somehow chains kind of complement nicely these this situation that you have with C and D, okay? And let me just tell you about the simple corollary. I hope I have some more time, yeah? So I should have probably told you in the beginning, but I'm kind of trying to think about how best to say stuff. So you can, of course, imagine arcs the whole time. So metric space is homeomorphic to the segment of reals 0, 1, say. Okay, and because I was drawing them as arcs, as you saw the whole time, of course. And what's the deal here? Well, it's simply a nice corollary of this theorem, because arcs are, of course, decomposable. They are chainable, which you can easily get if you take a decomposition or chain that covers 0, 1, and then just copy them over via the homeomorphism that you took, okay? And if they turn out, of course, they're continua, right? And if you're lucky enough to have them also be semi-computable in the sense that we were talking about, then our theorem is going to be applicable. So you will be able to find 2 computable points and the sub-arc, so that you know this sub-arc computably approximates the arc that you had in the beginning. Maybe just one more thing. So I actually did sort of a, let's say, rehearsal of this talk for our seminar, where I had a 10-minute long explanation of how to prove that S hat is a computable continuum. So if you're interested in those 10 minutes, you can ask me and I'll provide you with the link to the video. Okay, this is all I had to say. Thank you.